Okay, this is chapter 8. I wanted to, we're going to, in this chapter is all talking about covalent bonding, which is the sharing of electrons. We're going to go over that in this video lesson 8.1. The first section is talking about defining what a covalent bond is. Okay, so these objectives, we're going to apply the octet rule just like we did with the um, ionic bonds. We're going to describe the formation of single, double, and triple covalent bonds. Define what sigma and pi bonds are, talk about the relative strength of covalent bonds in relation to the bond length, how close or far apart the bonds are to the nuclei of the atoms, and the bond dissociation energy. I'm going to go over all this vocabulary here, and the main idea is that atoms gain stability when they share electrons and form covalent bonds. So again, atoms gain stability when they share electrons and form covalent bonds. Lower energy states make an atom more stable. So when they share these electrons, they enter into a lower energy state and become more stable. Gaining or losing electrons makes atoms more stable by forming ions with noble gas electron configurations. That was all chapter 7 stuff. And now in chapter 8, we're going to talk about sharing valence electrons with other atoms. Can also result in a noble gas electron configuration. So they can get to the noble gas configuration by losing or gaining the transfer of electrons or sharing. So in these non-ionic compounds, they share electrons. This chemical bond is called a covalent bond when they share electrons. And we call that a molecule instead of a compound. It's a compound when it's ionic. It's a molecule when it's covalent. Okay, so diatomic molecules, and there's these 7 that you need to know that are diatomic. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So hydrogen, nitrogen, and oxygen. Nitrogen and oxygen make up the atmosphere, and the halogens from fluorine down to iodine all exist because these 2 atom molecules are more stable than single atoms. So these atoms all need to exist in a more stable configuration, and they do that when they bond with each other. And this little illustration here shows what's going on when these atoms share electrons. There's the force of repulsion between the 2 positive nuclei, and then there's the force of attraction between the when the electrons are shared. The electrons want to share to get that 8 octet. Most stable arrangement exists at the point of maximum net attraction when the atoms bond covalently and form a molecule. So we have 2 fluorine atoms here, and they are sharing 1 electron. They have 7 here and 7 here, and they each share 1 electron. Okay, so this shared electron makes a total of 8 electrons around each atom, right? 6 unshared, right? And 1 shared pair in this electron configuration with the fluorine molecule. Okay, when only 1 pair of electrons is shared, it's a single covalent bond. Hydrogen forms, it just needs to get to 2 electrons in its outer energy level, right? Because hydrogen just has the 1 electron, and to get to 2, that's more stable than 1. So hydrogen bonds with itself. Each of those hydrogen atoms share a single electron, so now it has an electron configuration like helium, which is more stable. We're going to talk about Lewis structures in depth in another part of this chapter. I think it's section 8.3. But for right now, we're just going to introduce them. And it's a way to symbolize how many covalent bonds we have here and the unshared electron pairs that also form around that atom or in the molecules. This shows an example of fluorine, which is a halogen, And the Lewis structure here has 6 unshared pairs of electrons, right? 3 pairs of unshared pairs um, of electrons, and the single line here represents a shared pair. So when you see a single line in a Lewis structure, that represents a single 2 electrons that are shared together. Atoms in group 16, the oxygen group, can share 2 electrons, right? They have 6 valence electrons. They need 2 more to get to 8. So the oxygen typically shares 2 electrons. Either shares it in single bonds, 2 single bonds like this with water, or it can also form one double bond where it shares both of its electrons with one atom. Ammonia is in the is nitrogen plus hydrogen. That's group 15. It has the nitrogen atom and 3 hydrogen atoms around it, each forming a single bond with that. So now the nitrogen has 2, 4, 6, 8, 3 shared pairs and 1 lone pair. Carbon, we didn't talk about carbon very much when the ionic compounds, because carbon almost always shares electrons. Okay, so it's great at sharing, not so much at giving or taking, because it only has 4 valence electrons. It needs 4 more somehow to get to 8. So most of the time carbon does that with covalent bonding by sharing. And the example here is with 4 other hydrogen atoms, each sharing their 1 electron with the carbon. So now there's 8 around the carbon and 2 around each hydrogen. Sigma bonds are single covalent bonds. That's what you need to remember here, and that these occur when the pair of shared electrons is in the area centered between the 2 atoms. So in this illustrations here with water, ammonia, and methane, they're the blue areas are the sigma bonds, right? The purplish pink areas are the unshared pairs of electrons that aren't shared with the other atoms. Okay, so you can see that around this this oxygen from water, we have 8 electrons, 2 unpaired electrons, right? 2 unpaired, 2 pairs that are unshared, right? These are unshared electrons, and it says 4 electrons that aren't shared, and 1 electron and 1 electron from the hydrogen. So the hydrogen and the oxygen each share. The oxygen shares its 2 single electrons with 2 hydrogen atoms. The nitrogen shares its 3 single electrons with 3 hydrogen atoms, and carbon bonds with 4 hydrogen atoms. Double bonds form when 2 pairs of electrons are shared with 2 atoms. This shows the oxygen molecule sharing 2 pairs of electrons, right? This is the Lewis structure. We have the 2 pairs of unshared electrons and the 2 pairs of shared electrons for a total of 8 around each oxygen molecule. Nitrogen does the same thing or a similar thing with a triple bond, right? Each nitrogen has 3 single electrons and 1 pair of electrons in its electron configuration. It's valence electrons. Okay, so it forms a triple bond and has the single unshared pair of electrons. So there's 8 around each nitrogen, 3 shared pairs and 1 unshared pair. We talked about the sigma bond a little while ago. Now we're going to talk about something called the pi bond. It happens when we have more than one covalent bond. Either it happens when we have a double or a triple bond, and it's just a way of sharing how the electrons are shared between 2 atoms. They have these parallel orbits and overlap and share electrons. It's also known as hybrid orbitals. A double covalent bond consists of 1 sigma bond and 1 pi bond. A triple bond consists of one sigma bond and two pi bonds. So you always have one sigma bond with each of these bonds, whether it's the single, double, or triple. You only have one sigma bond. If you have a double, you add a pi bond. If you have a triple, you add two pi bonds. So that's what you need to memorize for the sigma and pi bonds. We're not going to get into it much more than that in this class. Covalent bonds, the strength of those bonds, how strong, tightly they're bonded together, depends on the distance between the two nuclei or the bond length. Okay, so it's an inverse relationship, right? As the length gets longer, the atoms are farther apart, the lower, the weaker the bond is. So as length increases, strength decreases. Closer they are, the stronger they are. Okay, so it takes some energy to break these bonds. That's called the bond dissociation energy. So the shorter the bond length, the greater the energy required to break it, right? The shorter the bond length, the closer those are together, the stronger the bond, the more energy it takes to break it. I have some numbers here for different atoms on how much energy it takes to break it. And you just know the numbers. We're not going to do too much with this. When in a chemical reaction, what happens with these bonds is that they, in the reactants, the bonds are broken. Okay, so it requires some energy to release the bonds, to break the bonds in whatever compounds or atoms that we are starting with. And then when these bonds reform into new compounds, energy is released when bonds are formed. Okay, so it takes energy to break the bonds. When bonds form, they release energy. Okay, so an endothermic reaction, this is a cold reaction, is one where a greater amount of energy is required to break a bond in reactants than is released when these new bonds form. So that would be like a cold pack. If we start the reaction, it has to take energy from the environment to finish that reaction. So it seems like it gets colder when that happens. It takes some extra energy from the environment to complete that reaction. In an exothermic reaction, the initial bonds are broken and then new bonds are formed. When the new bonds are formed, they release more energy than what it took to break those original bonds in the first place. So when that happens, heat is given off and we have an exothermic reaction. Okay, so that's it. That's the end of the video lesson for today. Hope you got all those notes. You can watch it again and get all the notes down and answer the questions on the web assign that go with this video. Thanks.